Good morning and welcome to your final installment of the periodic table of the elements. Yes, today is it. We're wrapping up the chapter, and the last thing we're going to look at, now since we started, let's do a quick review so we know what the heck we're talking about, because we started with Mendeleev and Moseley, right? Mendeleev was atomic mass, great, left some blanks, great predictions. Moseley discovered protons, lined it up according to atomic number, discovered the law of periodicity, right? Like chemical and physical properties, like repeated. What happened after that? Right. Then we kind of got to the idea of like types of metals, like metals and non-metals. Metals being solid, they conduct electricity, they're malleable, they have luster, they're ductile. Right? And remember, all these metallic properties come from highly mobile valence electrons. Then we talked about non-metals, right? And these are both separated by the squiggly line. Non-metals are typically brittle. They don't conduct electricity or heat very well. Basically, anything that a metal is, the non-metals aren't. It's like the opposite, right? That's why they call it non-metals. And way at the very end, we have the noble gases, and we learned about protons and neutrons and ions being like electrons being gained and lost and all that kind of good stuff. Oh, and the trends. All right, because we were left with columns or families where like all the atoms had the exact same number of valence electrons, and then we had periods or rows, and that's where they all had the same number of shells, and that sort of like lined up the trend in atomic radius, right? If you remember that, we made the chemist tree, like small at the top, very big at the bottom. The smaller they are, the more proton pull they have. The bigger they are, the less proton pull they have, because they're like, they're like farther away and stuff. I'm sure you guys remember that. Same thing with the period, right? Every time you take a step to the right, you're adding another proton, which squeezes it in. So from left to right, it went smaller and smaller. Same thing. The bigger the atom, the less the proton pull. The smaller the atom, the greater the proton pull. And then we defined electronegativity and ionization energy, right? Remember that? Yeah. Awesome. Yeah. Electronegativity very high at the top, very low at the bottom because it's all small. Big proton pull. Same thing with ionization energy, exactly the same. And in a period, if you're over to at the left, it's going to be less than it is way over at the right, because it goes right. It gets smaller over at the right. The atomic radius. The atomic radius gets smaller, and therefore you have more proton pull. And so because you have more proton pull, you have a greater ionization energy, and you have a greater electronegativity. I think that was it, right? Yeah, awesome. Okay, so what we're going to look at today are the properties of groups, or like groups of elements. Because if you look at the table, there's like group 1 and 2 make like a tall column of a chunk, and then there's the transition metals, and then you have like that block of non-metal-y kind of things, right? And then you have the halogens, which are at the very, like almost at the very end, group 17, and then the noble gases. So we're going to break those down, and we're going to look at some of their basic properties, okay? So we can kind of like get an idea of what those, like I said, like before, you can tell what the physical and chemical properties are of an element based on where it is on the table. And here is the summary of that. So, properties of the group. So here's the deal. Groups 1 and 2. Man, these things are more, like when I say group 1 and 2 are more reactive, I mean like, whoa, dude. These things are highly, highly, highly reactive. Now, group 2, it is definitely active. These are definitely active. Pause. Okay, so like I was saying, the alkali earth metals, right? This is group 1, more reactive, or like very. And also alkali earth metals, these are also very reactive. But these guys are more, like the group 1 is more reactive. Like when I say more reactive, they're downright explosive. And what we're going to do is we're going to take some sodium and we're going to plop it in water, and we're going to look at what happens. What we did before is we looked at calcium. Calcium was group 2. I don't know if you can see right there, but we're going to do sodium, which is group 1. It's awesome. So here's the thing about groups 1 and 2, the alkali and the alkali earth metals. These things are unbelievably reactive. Like, whoo! And they will never be found in elemental form in nature. You are never going to be walking through the woods and bump into a chunk of calcium. It just doesn't happen because group 1 and 2 are so reactive. They're always found in ionic form. Now, why is that, you might ask? Well, they're way off to the left of the period. And what that means is the atomic radius is relatively big. And so because the radius is relatively big, those electrons that are floating around the outside, they're barely being held on. So they just fall right off, like instantaneously. The instant they're an element, the electrons just fall off and they make ions. However, I'm going to jump down to this one here, is that even though they're like very reactive, once they react, they make incredibly stable compounds. The reason being that, like, once they get rid of that one outside one, that one or two, they have 8 valence electrons and they are dead solid stable, and they don't want that other electron they don't want their valence electrons back, because they can barely hold on to them, right? And again, it's all because of the radius. And now the activity increases at the bottom of the family, because if you remember, atomic radius goes like this, right? We have small at the top, then it gets bigger and then bigger, kind of like a snowman. So at the bottom of the family, we're looking at a really big radius. And the bigger, so like literally at the bottom of family of group 1 and 2, the electrons fall off. They can barely stay in elemental form, like all by themselves. Does that make sense? And so when we say low electronegativity and low ionization energy, what I actually mean is that it's almost non-existent, like it's almost not even there. Does that make sense? Oh, and this is one other thing that we like to do. Groups 1 and 2 will be M, because they're a metal, and when they bond with chlorine, they make chloride salts to make MCl or MCl2. Now here's the deal. Chlorine, and I want you to like lock this in, guys. Chlorine will always be a -1, right? So if you only have one chlorine, that means this is from group 1, because it's going to be a +1. Yeah? I hope you're following that. Now this has 2 chlorines. Now each chlorine is going to be a -1, and we have 2 chlorines. How much minus charge do we have in all? That is true. We have a -2 in all. And if there's only one metal, that means this metal has to be +2 in order to balance the charge. Right? We're going to go over this like in much deeper detail, like in subsequent chapters. But for right now, that's what we need to know. And this is always +1, because group 1s are always +1. This is always going to be like +2, and group 2 are always +2. So this is from group 1. And this guy is going to be from group 2. Dig? Doug. Awesome. Let's bump over to the transition metals. There are only 2 things that we really need to know about transition metals. They are stable. In other words, they don't react. These are things like titanium. Man, dude, we make fighter jets out of titanium. That means it's going to be pretty stable. I hope, because we don't want like the bodies of a F-15 or F-14 to spontaneously like burst into flames while they're zipping through the sky. All right. So the other thing that we need to know are the colored ions. All right. When these guys, when the transition metals. Now remember, this is the long, skinny group. So remember, we have group 1 is a tall column, group 2, and then 3. What is it? 3 through 12. Oh, I'm genius. Group 3 through 12 is this long, narrow column. So these are your transition metals. These are the group I'm talking about right here. They form very colorful ions. Anytime you see clay, ceramics, or pottery, right, the colors that come from that are almost always from transition metal ions. And that's all we need to know about these. The chemistry of these guys can start to get pretty complicated. We don't care. Basically, if you have a compound, in this class, if you have a compound that has color, the color is going to come from the transition metal. Full stop. Got it? So if I'm like, hey, which of the following compounds has color? Or there's 4 compounds. One of them is very colorful. Why? You say because the ions are from the transition metals. Or if it's like, here's a list of 5 different compounds. Which one's going to be colorful? It's the one that has an ion from the transition metals. Groups 3, that's a 3, through 12. That's the worst 3 I've seen in a long time. So groups 3 through 12. Okay, got it. Awesome. Any questions? No? Well, if you do, Bring them to class, and then I'll answer them, because this is really hard to answer questions from like right here. I'm not going to even lie a little bit. So next one, groups 3 through 16. Now these are the non-metals. Now remember, you got group 1, you got group 2, you got your transition metals, and then you have 3 through 16. Here's 17, here's 18. So we're talking about this block right in here. It's where we have like the squiggle line, right? But we're gonna focus on our non-metals here, okay? Now for these guys, the activity, or like the degree to which it reacts, like whether it reacts violently and quickly or it's like slow and steady, increases as you go up the family. Now, watch, I want you to notice something. Here, for number 2, it says for groups 1 and 2, remember the metals, the activity increases at the bottom of the family. Now that we're at the non-metals, it's going to be up here at the top of the family, right? So this area, this zone up in here is where we're going to get the most reactivity, okay? And also in this group, at the top, we're going to have non-metals, right? Right here is going to be like a non-metal, but once you get down here, you transition into metals. So this block, these families have like the wildest range of chemical properties out there. At the top you'll have oxygen, and at the bottom you have a metal. Like that's a pretty wide range. Whereas groups 1 and 2, like these guys are metals and these guys are metals. That is shiny silver, that's shiny silver. This is a gas and this is a shiny silver metal. So it's like groups 3 through 16 have like pretty radically different like characteristics. Any questions? No? Really? You guys are like really digging this in. All right. So group 17 are halogens. Man, sakes alive. Halogens. All right. So group 17. These guys. All right. Group 1. Group 2. Transition. What's that? 13 through 16. Group 17, these guys right here, the halogens. Okay, so here's the deal. Do you remember way over on this side of the table, these metals are very, very reactive, and these guys right in here, these are not so much. Well, what do you think these guys are on the other side? I'll give you a minute to think. All right, so these guys over here, that's enough thinking for one day, thank you. These guys over here, these are very, very reactive, because they lose electrons. They have very low electronegativity. The atomic radius is relatively big, right? Now, as we move over this way, the atomic radius is getting very, very small, relatively speaking. So because these guys are so much smaller, they have so much more proton pull. And they are very, very reactive for the exact opposite reason. Like these guys over here, or maybe there, I can't tell which way I'm pointing, but these guys are highly reactive because the electrons just pop right off, man. Their electronegativity is like next to nothing. Same thing, only completely opposite. These guys over here, these are incredibly reactive because the radius is so small. The proton pull is like through the roof, man. These things are so small, they just rip electrons off of anything. They shred atoms and molecules to pieces by ripping electrons off, and they gather it up to themselves. So the halogens are highly reactive for the exact opposite reason that group 1 and 2 are reactive. Okay? So these guys are indeed very, very, very reactive, and these are also never found in nature in elemental form. They're always found in compounds. Always. Always, always. Why? Because of their unbelievably high electronegativity and ionization energy. It's the exact opposite of our like alkalides and alkali earth is. Earth is. Need another cup of coffee. Anyway, so again, the halogens, they're so crazy reactive because they have such a high electronegativity and high ionization energy because their radius is so wee small. They gain electrons, right? Because that huge proton pull, as shown by high electronegativity and high ionization energy. These guys gain electrons, right? So these guys are always going to be negative. These guys are always going to be positive. So the halogens are always negative because they have such a high electronegativity. Like just always. Always. Oh, and here's one other little like trippy thing. Oh man, I'm messing up so hard. Well, I messed that all up, didn't I? You know, some days you win, some days you lose. Right now, I seem to be not winning, and that's okay. I'm not scared. Are you scared? I'm not scared. So look, I'm going to redraw this thing, and it's going to be messy, so give me a quick moment. There's your transition metals. Here's my halogens. Let's just pretend that these are halogens. Man, these are up here. These are gases. The first two are gases. Then you have a liquid. All right, so remember, like bromine and mercury are the only two elements that are liquids. You got to remember that. I don't know how many times I've said that. You have to remember this. Bromine, mercury are the only two liquids. So fluorine and chlorine are gases. So fluorine is here, chlorine is here. Bromine is a liquid, and then the next two are solids. So you start as a gas. This is the only group that does this, where you have a gas and a liquid and a solid. You pass through all three phases of matter. No other group has all three phases of matter. Like, none of them. It's just kind of weird. I want you to lock into this. Maybe remember this for like later on, because I guarantee you we're going to be like digging into why is that? Because somebody once went, wait, what? That doesn't make any sense. Why is this group so different than all the other groups? Well, we did indeed find out why. So again, fluorine and chlorine are gases. Right? Then it goes to a liquid, then it goes to a solid. So as the atoms get bigger and bigger, they go from a gas to a solid to a liquid. Got it? Good. All right. Finally, last but not least, our noble gases. These guys, okay, there's group 1, there's group 2, transitions. We have our nonmetals, we have our halogens, that's group 17. And now this guy at the very, very end. These are the noble gases. Here's what we need to know about them. They don't do anything. They don't react at all. Because these guys all have 8 valence electrons. So they're good. They're done. Like, why would they react if they had the magical 8? Like, they're done. Like, who... Like if you had all the perfect bling, why would you want to get somebody else's bling? I mean, your bling is the blingiest of all the bling. So they got the 8 blingy electrons, so they're super duper happy. So they don't react with anything. They just sort of float around. Like they don't even bond to themselves. They don't even make a lump. They are noble gases. They just float through space. And they are monatomic, and I'm sure you can dissect this like word to know what it means. That means one atom. They're one of the few things that show up only one atom at a time, always, which is pretty weird. I mean, it is what it is, but it's just different. It's like they're like the only ones that actually do that. So the next thing we're going to do that I want to look at are the diatomics. Remember, diatomic, the di, that's 2 atomic atoms. These are ones that always show up in pairs of 2 in elemental form, because we're talking about elements on the periodic table of the elements, right? So this is, remember, Nafkolbre. Right? Nafkolbre. I tell you, it does. It reminds me of some old British lady having some kind of like treats with her like English little tea, little Nafkolbre biscuits. Or, you know, there's the N over down. And don't forget the H. Because that's a simple trick to help remember diatomics. Because you must have these memorized. Because there are going to be questions about diatomics throughout the entire year. When I say things like oxygen reacts with carbon, you're going to have to be like oxygen. Done. Like, you got to have oxygen as a diatomic. Same with fluorine, chlorine, bromine. Oh, look at that. That's like a lot of the halogens. Right? Yeah. Okay. So... diatomics, monatomics, lock them in, and one last thing before we go are these Bohr diagrams. I'm tagging this on here just to like help us like visually see what happens when things become ions, when things lose their shell. And we talked about this before, but I'm just going to dig in a little bit more. It is a simple model that helps us visualize atomic structure. And here's how it works. The first thing we do to draw a Bohr diagram, a Bohr diagram, is we take a circle and in it we write the nuclear charge. So for this one, the nuclear charge is going to be 11. That is a sodium. You dig? And so the next thing we need to do is go back to our periodic table of the elements right over there and find the electron configuration for sodium, and it is 281, and that tells us that there are 3 levels. So we draw 3 shells or energy levels or principal energy levels or primary energy levels or whatever thing they come up with, and in the first shell, the closest, there will be 2, so I put 2 dots, and we're going to try to keep the dots as far away as possible because remember, these are negatively charged, so they don't want to be right next to each other. They're there, and they are physically pushing each other away. In the next shell, we have 8. So it'll be 1, 2, 3, 4, 5, 6, 7, 8. Trying to get them as far apart. And then in the last shell, it'll be our 1 solo right there. Okay, so that's the Bohr diagram. Again, you draw a circle for the nucleus and write down the atomic charge, or I'm sorry, the nuclear charge, not the atomic charge, the nuclear charge. And again, the nuclear charge is just the number of protons, right? Because it's the charge in the nucleus. That's why we say nuclear charge. And that's just like the atomic number. And then we go get the electron configuration from the table. And then in the first shell, we put that number of electrons. In the second shell, we put that number of electrons. In the third shell, we put that number of electrons. And there we have the Bohr diagram of sodium. Lovely. Now, when we make an ion, here's sodium Na+. So here's the thing. Here's sodium, 281. Here's sodium +1. So the fact that this is a plus sign, right, this indicates that we are going to lose electrons, right, because it's positive. And since it's 1, we're going to lose how many? We're going to lose 1 electron. And remember, when we lose electrons, we lose the entire outer shell. So this whole shell is gone. So our new electron configuration is 2, 8. Does that make sense? Like, and we don't get, like, we're not given the electron configuration of ions. We have to, like, look at the electron configuration in the ground state from the periodic table, and then we have to look at the charge of the ion to determine what's up. And so just like before, it's sodium. It's got a +11 in our nucleus, right? And then our first shell has 2. Our second shell has 8. 4, 5, 6, 7, 8. And you can kind of see, like this one, the atom is bigger than the ion. Because as you all know, the ion has lost its outer shell. The outer shell is just gone. And that's why it's smaller. So this is called a Bohr diagram. Again, it's a simple model for an atom. And now that we're like done with all the things about atoms and whatnot, we have a little diagram for it, which is fun. And then we're done. Like, we're totally done chapter 2, which is awesome. Except for that means exam is coming. Well, first we'll have a quiz, maybe. This time we'll have a quiz and then an exam. But before we do that, we are going to work on periodic table on Mars. The way this one works, guys, is like basically we're gonna pretend like we go to Mars and find all new elements, which is not the case because all the elements in the galaxy and the universe are all the same. But let's just pretend the elements are different on Mars. But the deal is they follow the exact same like laws of nature. So all the trends are the same. It's ordered the same. Shells, valence electrons, all that stuff, and we got to fill that periodic table. And until then, and when I see you, I hope you guys have an awesome day. I know I will.